Welcome you all to today's class. In the last two classes we have covered one-dimensional lattice and then how to construct from one-dimensional lattice, two-dimensional lattice, what are the symmetry elements associated with it, what are the types of crystal structures which we can have or planar groups which we can have. Today we will talk about how to generate two-dimensional lattice, from a two-dimensional lattice, how to generate a three-dimensional lattice, okay. What are types of point groups and space groups which are associated with these lattices. Okay. We have to follow the same procedure which we have done for generating the two-dimensional lattice, okay, from one dimension. That is, take a two-dimensional lattice, keep it on top of one another at some particular angle or some specific positions with respect to the lattice which is kept below, okay, and try to generate a lattice and see how many types of lattices which can be generated. But there are many positions we can keep it one lattice on top of each other, but the distinct number of space lattices which we will generate are only 14. Okay. We will take a few examples and illustrate how this is being done. One I will take with respect to a hexagonal lattice, okay, and how different types of lattices could be generated. The other example which I will take is essentially a parallelogram, okay, that is oblique lattice, and from that what are lattices which could be generated. What are types of how we can generate a Bravais lattice from hexagonal lattice we will consider. What have we done here? Essentially, this, if you look at it, it is a hexagonal lattice, okay. One lattice is what is where the lattice points are marked as A, okay. This is the hexagonal lattice, in which if we kept another lattice on top of it, okay, the lattice points which it can come is that this lattice can be called as the B lattice, which is kept at this particular position. That is, on a hexagonal lattice, if I consider it, here this is one particular position where the next layer can come, or this is another position where the next layer can come, okay. If we keep at this particular position, B layer position, and the next layer on C layer position, and the third layer if we keep it, it will be kept on this one, A, B layer, C layer, then the A layer will come. So this is how the layering sequence is, that is first layer, second layer, third layer, fourth layer. So if we consider it, this way we can generate a space lattice can be generated. Okay. What, depending upon the distance which we choose it, from here if we consider it, this is this distance it is called as S here, okay, and then at what height the next layer is being kept, okay, depending upon that various types of lattices can be generated. Okay. If we keep the B layer at a distance which is h is equal to 2s by root 6, okay, then this stacking sequence will generate an FCC lattice. Okay. If we keep the B layer and all the successive layers at a distance which is h is equal to like s by root 6, okay, then we can generate a simple cubic. If we keep the distance between the layers, okay, such that h, the height is equal to s into s by 2 into root 6, then we can generate a body centered lattice. If we choose a value of h which is different from any of this value, then we generate a trigonal lattice. Now you can understand that using the same hexagonal lattice, at what positions, that is the stacking sequence is ABC, ABC type of a stacking sequence, but the height at which these lattices are, this each of planar lattice is being kept with respect to one another, we can generate either trigonal, simple cubic, or body centered or face centered Bravais lattices can be generated. If we keep on top of an A layer and another A layer, okay, we generate a hexagonal lattice. So all these lattices could be generated from just two-dimensional hexagonal lattice itself. Okay. Suppose we take a lattice which is an oblique lattice. Okay. It is nothing but a unit cell is a parallelogram. If we keep this parallelogram one just on top of the another, then what we generate and keep the distance such that it is not equal to neither the translation vector A nor the translation vector B, then what we generate essentially is nothing but a monoclinic lattice. If we keep the next layer so that this lattice point is at some position, okay, the projection of it at some position which corresponds to a random point in the lattice, and the lattice parameter in that direction, okay, is not equal to neither A and B, we generate a triclinic lattice. Okay. And if we keep these lattices in such a way that we capture some particular one, the next lattice, but at a position which is halfway on the x axis, okay, just above it, then this is, you can see that this the next layer which is being kept, okay, and then the third layer which is being kept is right on top of the first layer. If we repeat it like this, now what we have generated is a face centered monoclinic lattice. So by keeping either at symmetry points or at random point, we can generate different type of lattices, but finally if we try to look at how many lattices which we can generate, there are going to be only 14. Okay. These 14 lattices are represented here. Okay. So generally the way these lattices are represented is with respect to A, B and C, the lattice parameters, and with respect to angle between them. Okay. Actually that is essentially a consequence of the type of symmetry which is associated with these lattices. Strict classification is on the basis of symmetry. That is, if we take triclinic, it has no symmetry associated with it. If we take monoclinic, it has one two-fold axis, rotation axis. If we take it orthorhombic, perpendicular to each of the axis there is a two-fold axis. Okay. If we take triclinic, there is only one four-fold axis which is there. If we look at cubic systems, there are 4 three-fold axes which are present. Okay. If we take trigonal, there is only one three-fold axis. Hexagonal is one which has got hexagonal has got one six-fold axis. So essentially what we have now is the 7 crystal systems which we call it is based on these types of symmetries. These are all the minimum symmetries which will be associated with these crystal systems. Okay. They can have a maximum symmetry, that will come to later, what is the maximum symmetry which we have. Okay. And we should always remember that hexagonal close-packed system is not a Bravais lattice. Bravais lattice is only hexagonal. Okay. It is the one which contains 2 atoms, 2 lattice points per unit cell, hexagonal close-packed lattice. Okay. And the symbols which we use here are primitive lattice is represented by P, I for body centered, F for face centered, R rhombohedral, A, B, C for the different face centering. Okay. But all are capital letters which are used, unlike in the case of two-dimensional lattice. Okay. In the next slide, in this particular one, all the 14 Bravais lattices are being shown. What I have tried to show here is that in addition to this one, what is the space group symmetry which is associated with this. I will come back to it later what these space group symmetries are, but essentially what the P represents is what is the type of a lattice which we have, okay, and what all the symmetry elements which are associated with it, that is what it represents. Generally the lattices, as I mentioned earlier, exhibits the full symmetry of the lattice. Okay, the maximum symmetry will be exhibited by all the lattices. Okay, that way here all the maximum symmetry which is associated is exhibited. One thing what one should always remember is that earlier case when we considered how if we put a motif around different planar lattices, okay, we are able to generate only uniquely some of them. That is, if we put a motif, asymmetric motif around whether it is a square lattice or whether it is a rectangular lattice, we generate only a one-fold symmetry. Okay, that gives an indication, okay, that irrespective of the value of A and B, the symmetry is the one which decides what type of a specific space group which it has. Okay, on that basis, that when we write A not equal to B not equal to C, it does not mean that it is not equal to A necessarily not equal to B, not necessarily not equal to C. That is what in crystallography term it means. Not equal to is does not mean not equal to, necessarily not equal to, it can be also. Okay. So, now let us look at what are the types of symmetry elements which can be. That is, before going into the details, we will just list these are all the symmetry elements, and then we will try to see how go into details about these symmetry elements. They are, one translational symmetry element will always be there with any lattice. Then we have a rotational symmetry element, okay, which we have already seen what are rotational symmetry elements. Reflection symmetry element which we had seen it. In addition to it, here we will have an inversion symmetry element also will come. Okay. Then in addition to this is all with respect to consistent with translation, but we are considering it a round-up point. In addition, combination of rotation and translation, combination of rotation and reflection, combination of rotation and inversion, all the three are possible. They will also, we can consider cases. So, these are all the cases which we will look at it. In fact, the combination of rotation plus translation gives rise to combination of rotation and translation gives rise to screw axis. Reflection and translation gives rise to glide. Okay. Reflection and translation will give rise to one is a glide which you get it. Okay. Then the other is rotation and translation gives a screw axis. Okay. Then rotation and reflection perpendicular to the rotation axis, if we consider, that will give rise to an inversion. We will come to it later. Okay. Okay. In this particular slide, we have just shown the three-dimensional unit cell, which is essentially like a triclinic structure, and any vector in this can be represented by a vector. Okay, R is equal to U into A plus V into B plus W into C, where U, V, W are the integers and A, B, C represents the translation symmetry. This way, in the vector notation, all the lattice points can be generated by taking various combinations of U, V and W. Okay. And what I have shown here is that various types of this one, because different types of notations are used, different ways it is represented in the books. Okay. About the rotational symmetry, I had already explained, okay, how this rotation consistent with translation put some restrictions on the type of rotations which are possible. So, I will not go into the detail, but in this slide what I had shown is that how they are represented on the stereographic projection. I had just given a brief idea without going to a detail anything about the stereographic projection, but that I will do it now. What stereographic projection is, how important it is. Okay. Because when we have to represent in 3 dimensions, what we would like to do is that when we talk of symmetry, angular relationships have to be specified, or the angular relations have to be shown on 2 dimensions, because 3 dimensions we can view it, but when we have to put a projection, okay, it is always in 2 dimensions we deal with. Okay. How do we go about and do it? Okay. There are various types of projections are there. The simplest is a perspective projection. In a perspective projection we can see it, okay, but the distance, unless we give more information, we do not know how far an object is far away. Okay. In a stereographic projection is a projection where it is from the angular relationship in 3 dimensions could be represented in 2 dimensions. Okay. Here I had just given what are the applications of stereographic projection. One, in the crystallography, okay, for showing angular relationship between different planes and directions, we can use stereographic projection. In X-ray diffraction, okay, when we have to represent texture, we require it. In electron microscopy, different orientation of crystals, their planes and directions, okay, between different interfaces, when we wanted to find out orientation relationship. In all these cases, stereographic projection is important. Then when we are deforming a single crystal, how the different slip planes are rotating, all this information we can get it using a stereographic projection, because there it is a 3 dimension what is happening, but we wanted the same angular relationship to be projected in 2 dimensions so that it is easy to do the calculation. What is a stereographic projection? The way in which we can understand it is that you take a sphere, okay. In a sphere, as we know for a globe, when we consider, there are latitudes, longitudes are there, we can have it. Similar to that we can have it in a globe. You assume that there is nothing else is there, okay. Fix the coordinate system at the center, okay, x, y and z coordinates are fixed, and then what we do is that take a point which is on the surface of the sphere. With respect to the z coordinate, it makes an angle theta, or the z coordinate we consider as the pole, okay. And if you look at the, if we view this from the other end of the pole, from the south pole, okay, the ray which connects our eye to this pole cuts the equatorial plane at some particular position. So this distance OP, if you look at it on the equatorial plane, okay, it is given by the formula r is the radius of the sphere into tan theta by 2, what the angle which this point P makes with respect to the z axis. Okay. So essentially using this relationship, all the points which are there on the sphere can be represented on the equatorial plane. Okay. If this point P rotates around this pole making an angle theta, it will be a circle, and the projection of it will be nothing but this OP will take a rotation, you take it a circle, so it will generate a circle. Okay. Similarly, you take this particular this one longitude, okay. This longitude, all the points on this longitude, the final projection will be nothing but it will be a line passing through the center. This will be clear from this particular slide, this slide. Here if you look at it, these are called as the great circles, are nothing but in the geography, if you look at it, we call it as the longitude, okay. This longitude, essentially you can see that all these projections pass through the center, and this is a line which passes through, okay. This is nothing but a diameter, okay. And these circles which are the latitudes, they project it as concentric circles, okay. If we assume that on the surface of the sphere we have marked at every 1 degree, 2 degree or 5 degree, it is some specific angular separation, latitudes and longitudes, okay, and then view it from the south pole. Then how will it look like? We will be generating a projection. This projection is called as the polar projection. In this projection, if I consider this particular one, it makes an angle 30 degree, this is a latitude which it represents. So if I take any particular position, if I fix the coordinates x, y, and this will be the normal to the screen is the z coordinate. Now we know that if I mark a particular position, I know what is the position of this on the surface of the sphere. Okay. So, essentially all the angular relationship in 3 dimensions are projected in this 2-dimensional projection. Essentially for stereographic projection, this is the polar projection which is used. Okay. This is, but only thing which is important, which we should and which we should note, is that if we consider, okay, in this particular projection, if we consider any point on the sphere, if it is on an equator, where will it get projected? It will get projected onto the circumference of the equator, correct? Right? If it is going to be anywhere on the top hemisphere, the projection will be inside the circle, equatorial plane. So, that is essentially, and when we consider a space lattice, okay, if we consider any planar directions, okay, it is going to be in 3 dimensions. So, anything that is in a 2-dimensional lattice, when we consider, it is only the equatorial projection which you have to consider. That is why the motifs are always placed on the circle. Here, since it is a 3-dimensional case, the motifs are all kept right inside the circle. Okay. So, if we take a motif like this here, if a mirror operation is there, we put a mirror along this x-axis, then it will be getting reflected, and this is how the mirror will be reflected in a 3-dimensional projection. In a 2-dimensional projection, this point would have been put here and this point would have come here. That is all the difference is. Okay. Mirror perpendicular to it, if it is there, now we can see that the circumference of the circle is made thick to show that this is a mirror. Okay. If it is an inversion operation, okay, that is the point on the upper hemisphere, invert it through the center, it will come into the lower hemisphere. So, anything which is on the lower hemisphere, when we show in the projection, the closed circle represents always motifs on the upper hemisphere, and the open circle shows motifs on the lower hemisphere. Okay. So, in an inversion operation, this is how it will take place. And if it is a 4-fold rotation, now we can see that a motif which is being kept here, the 4-fold rotation. This is how in a stereogram the various types of rotation and reflection and inversion symmetry operation could be, or rotation and a mirror which is perpendicular to it, all this can be represented. All the examples are present here in this slide. Okay. So, this is about symmetry representation, but when we have to find out the coordinates associated with any one of them, okay, all the motifs which are generated, if we are given a coordinate x, y, z, we should know what is the transformation matrix which is associated with it, each of this symmetry operation, and then we can find out, okay, using the formula which I had given earlier in the last class, one can generate various types of points. Okay. All the corresponding symmetry related points could be generated, okay, whether it is for a rotation or whether it is for a reflection or whether it is for inversion. Okay. Here for different operations, this is for an one-fold rotation, the matrix, this is the matrix which will be there. If it is one which is a 2-fold rotation, okay, then this is the type of a transformation matrix which we will use it. If it is a 4-fold rotation, then this is the sort of a transformation matrix which you have to use it. But also we have to define that whether it is a clockwise rotation or an anti-clockwise rotation. That is also very important. With this, what we have looked at it is what are the various types of rotations which are possible and how they are represented. Now, can we have a combination of this, just the rotation itself, axis? Suppose I take a 3-dimensional lattice, like for example, I have taken a orthorhombic structure. Okay. In this, along each of these axes, along this axis or along this axis or along this axis, all these axes we can have a 2-fold rotation. Okay. So, what is being done is that if I represent a twofold axis on the surface of a sphere, because this is the origin O, okay. So around this direction or around this direction, along two directions I find out some sort of a rotational symmetry. What is the third direction in, you identify another third direction where what is the type of symmetry which exists. Okay. These are all the combination of symmetry elements which are possible. So if I take that is 2 and 2, okay, and then if on the some other direction I find a twofold rotation, okay, then what is going to happen is that between the two axes which have twofold rotation, all the axes, each of them taken separately 2 at a time, we find that angle between them is 90 degree. And then that structure is orthorhombic. Suppose the two operations, okay, it is there. In another direction you find that a threefold. Then the crystal system becomes a trigonal one. Then the angle between the two axes twofold will be 90 degree and the other one is turning out to be 60 degree. These various combinations are possible. On that basis we can have different types of crystal structures also. Okay. This is one way in which various types of crystal systems could be classified. Okay. So essentially what means that these are all the unique combinations which are possible by combination of just rotation alone, right. Okay. Now in this particular slide what I had shown here is essentially that the different crystal systems, okay, based on how they are defined, based on symmetry and what is the minimum symmetry which is necessary for these Bravais lattices, okay. And also the for a conventional cell, if we consider what are the relationship between the angle between the axis and the translation vectors, okay. This all of you have studied also earlier itself, you are very well aware of it, okay. Now about reflection I had already explained, so I will not go into the details. Now let us look at the inversion symmetry, okay. So far I have not talked about the inversion symmetry. That is, if we take with respect to the unit cell or the crystal lattice, if we take any point R, okay, by an inversion the R will become minus R. So all the coordinates will become x, y, z will become minus x, minus y, minus z. So for this the operation, the transformation matrix which will be is this particular type of a transformation matrix which has to be used, okay. So essentially if you now look at it, what are the types of point group symmetry operations which are there in 3D lattices, okay. Rotation which we have considered, reflection which we have considered, inversion is one, okay. Then we can have a combination of rotation, it is possible. Then rotation and an inversion, we can take that combination. Rotation and reflection also we have considered, right. That is either that rotation axis is there, the mirror is reflection is parallel to it or perpendicular to it, that combination can be chosen, okay. Then we can have a rotation and a reflection, okay. That is rotation and a mirror perpendicular to rotation axis, that gives rise to inversion. That is why sometimes inversion is called as, is it a new operation or is it a combination of two operations of rotation and reflection, okay. Then in these things what we have to look at it is that if we take only a rotation, okay, what is going to happen is that suppose I take this object, okay, by a rotation it will come like this, it will go like this, always it creates one particular type of an object. That is, if I take a right hand, I rotate it like this all the directions, only the right hand gets rotated. But during this rotation operation, right hand motif can never become like a left hand. Reflection and inversion are the operations where that is enantiomorphic structures where the by this operation the right hand is generated into a left hand operation. Okay. This has some significance in the behavior of the material, which I will not go into the detail because that is not particularly for the defects in material, one does not have to bother about it. Okay. So, as I have mentioned, using stereographic projection we can represent it. Here all the basic symmetry elements, especially the point group symmetry elements are. So, the combination of rotation, reflection and inversion and roto-inversion, these together constitute the point group symmetry. Okay. So, this can be represented in a stereographic projection. Okay. In this it is for one fold, okay, and then two-fold. Okay. That symbol which is used to indicate that it is a two-fold rotation, okay, and a three-fold rotation we can see that a motif which is being placed here, okay, that three-fold rotation it generates. Like that various symbols are being used. I will not go into details of any of these symbols because International Linear Crystallography table, if you look at it, all the symbols are explained very nicely, okay. And in many of the books which I had mentioned earlier also, in those books also all these symbols are explained. Essentially what we can make out is that these are all the just pure rotation, and this corresponds to roto inversion, this layer, and this layer if you look at it, it is mirror which is parallel and another is perpendicular, okay. Then this is just a simple inversion. So, these are all the basic operations and various combinations which we can choose of all of them. Then you can imagine how many combinations which we can have, okay, generate many. But how many distinct ones finally we find it, like in the case of two-dimensional lattice we did exercise, then we find that only 10 are going to be there, point groups, correct, planar point group. Similarly here it is going to be only 32 distinct point groups are possible. So, essentially what is point group is essentially the various symmetry operations like rotation, reflection and center of inversion consistent with translational symmetry, okay, and roto, and their combination, roto combination is called as a point group symmetry, okay. Many, as I mentioned, many possibilities exist, but distinct ones are only 32, okay. Why do we require a study of this point group symmetry? Yeah, why it is very important? This is because when we look at the properties of the material, okay, change in different directions or on different surfaces. If you look at it, if a crystal grows, you find that it grows with some particular morphology. Earlier all the point group symmetries were found out by looking at the morphology of the crystals. Similarly, electrical conductivity, okay, thermal expansion, all these are, and different directions can change depending upon the crystal structure. They are related to a point group symmetry. How experimentally we can find out is by measuring these properties in different directions, we can determine what all symmetry elements are associated with it, okay, or essentially the point group symmetries can be done. But the space group symmetry, if you look at it, which involves others like screw axis, which will come shortly, it is going to be externally, it is very difficult to see because it is only associated with that only a translation, which is very, so the translation it will not show us a change in property in a particular direction, okay. So, what is important is that study of point group symmetry is important because that gives information about the properties in various directions in crystal structures. In short, what we can have is that 32 point group symmetries, okay. Just the combination of all the symmetry elements which you consider, they are 11 are there. Roto inversion gives another 5, okay. Then combination of proper and improper rotation axis if you consider, altogether another 16. So, in short 32 are generated. In this slide, I am just showing how they are in a stereographic projection they are represented, okay. I will give some assignments, one can work it out how to generate given the point group symmetry which is given, how this stereographic projection they are generated, okay, how they look like. Okay. Then one will understand how this has been generated actually and presented in various books. Now we will go into the International Union of Crystallography table. If you look at it, one, a stereographic projection which is being given. This is the case which he has considered is 4 mm point group. Okay. In this particular one, in addition to giving this the position of the motifs, okay, the general motif, what are other positions if the motif we keep it, also the same symmetry element will be can be represented. Like for example, if I put one at the center that has got a 4-fold symmetry, so I do not require 4 motifs to present them, only one at the center is good enough. Okay. That is how what is being essentially explained here, like the way I explained earlier for 2-dimensional lattice. Okay. Here also what is the side symmetry associated with it, okay. Then the Wyckoff position and the multiplicity corresponding to the particular side symmetry. And here it is not represented in X, Y, Z, it is given in terms of planes, because most of the symmetry elements earlier has been, when the plane groups, point group symmetry, if you try to look at it, okay, some directions we are looking at it, the planes which are perpendicular to them, that is what it is being represented. Okay. So the symbol which is used to represent is planes. Okay. Then in this side what I had shown it is that for the general one, okay, position, exactly if we put one motif around it, how the other motifs will be generated for this particular point group symmetry. One 4-fold rotation which is taken here, okay, that is this point is rotated from here, it comes here, then from here, now from here to here to here to here it comes, and then what we do it is that put the symmetry elements, mirror symmetry you consider it, then you find that get reflected. Okay. Suppose on the symmetry axis, okay, on this if I place it, only 4 points have to be placed here. Okay. Still that 4-fold symmetry and mirror, all these symmetry elements are. If I place it around this axis, okay, the symmetry element, mirror symmetry elements which are there, then I have to place at only 4 positions. Okay. If I place it at the center, only at 1 position. So this is essentially what is being given, 1. Okay. This is corresponding to general, this is corresponding to one mirror, this is corresponding to another mirror, how the various planes will come, this is corresponding to the third one, 4th one, correct. Okay. These various 32 crystallographic point groups, okay, they correspond to 7 crystal systems which are there, we can group them. Okay. So triclinic has got 1 and 1 bar. Okay. Monoclinic, if you look at it, it is 2m and 2 by m. These are all the point groups which are associated with it. In this, if you look at here, what is essentially is being given here is the minimum symmetry elements. In this side, what is marked with the pink color shows the lattice which will have the maximum symmetry elements. Okay. That is how I have just identified, marked it. Okay. So trigonal will have 3, okay, but if we take as the trigonal as a lattice, it can have 3 bar. That is, if we have a crystal, at least it should have a 1 3-fold axis. Is it clear? Okay. And then another is that here some symbols are being used. When we use M3 bar, this is essentially it's a short form. It actually corresponds to 4 by m, 3 bar and 2 by m. Okay. Then the next question comes is that what is the convention which is being used to represent these symbols? Is there any convention which is being followed? Otherwise, we don't, in one case we triclinic use only 1, monoclinic we use 2, okay. Here 3 symbols are being used. In which directions are where, which direction along which these symmetry operations are performed. That is given in this slide. Triclinic, if you look at it, we do not have any symmetry operation, okay. There is nothing like a primary or a secondary. If you take monoclinic, Okay. Always that 0 1 0, the B axis is chosen for the show the two-fold symmetry which is present there. Okay. Orthorhombic, if we see A, B, C all have got a two-fold. Okay. So essentially what it represents is these are all the symmetry along various axes. When we say 2 that means that two-fold along the A axis, that is primary is then secondary is mirror along this direction, then another is along this direction mirror. So that will be, so 2 2 2, and here if we look at it, tetragonal, okay, 0 0 1 is shown along the primary one. So the first letter represents a 4, okay. Then the next one represents secondary, that is what is the symmetry along 1 0 0 or 0 1 0, and the third one, the third letter represents symmetry along 1 1 0 direction. Like cubic, if you see it again, that on the primary one represents the symmetry which is along the x, y or z axis, and the second letter represents the symmetry along 1 1 direction, and the third letter represents the symmetry which is along the 1 1 0 direction. Okay. If we take 4 3 2, that means that fourfold along any one of the A, B or C axis, and 3 is along the 1 1 1 direction, and the twofold along 1 1 0 direction, right. So from this one can very clearly understand how, what is the sort of coordinate system which is being used to represent the various symbols which are given here for the 32 point groups. Okay. Having looked at these 32 point groups and their representation, how it is done in stereogram, okay. If you try to generate a space group, what we have to do it is that point group is around a point which we are considering it. Space group means that around the lattice, if we are trying to put motifs having this sort of a point groups around each of them, what are the distinct types of crystals which could be generated with having specific symmetries associated with them. Okay. Is there, here again the combinations, if we try, many are possible. Distinctly, finally we find that only 32 space groups are possible. Okay. We will not be going into all of them, but before going into them, so far we considered only point group. If we consider as a lattice, okay, or what we have not done is that we have considered between rotation and reflection, which is consistent with translation, but we have not combined it with translation. We can combine rotation and translation, okay, and we can combine mirror and translation if we do it. In the lattice, they generate some special symmetry elements. Okay. For example, if we combine rotation and translation, it generates a lattice which we call it, the symmetry which it generates is called as the screw axis. Correct? For example, here if we look at it, okay, example, if we take this is a 6-fold, okay, you know that 6-fold means that 60-degree rotation has to be given, okay, and then a translation by some vector or some pitch, you that is you rotate it and then translate it along the screw axis by some vector of magnitude, you take tau, okay, or a pitch which is tau. Then after n rotations, okay, we should be able to come back to original position. What is the position which will be coming? It could be either equal to the lattice translation vector if it is t, or it could be some multiple of t. That is what essentially written n rho equals p into t. Okay. This is equivalent to, like example which we can think of in real life is spiral staircase. When we go on a spiral staircase, there is a pitch with which it's being, the staircase it rotates, and finally afterwards it will be coming back to original position, again it rotates, correct? So depending upon the how many times it gives, we have different types of combinations which are possible. One, here the pitch which is taken is, if we take 1/6 of the lattice translation vector for a 6-fold, that after every rotation by 60 degree, we move it by 1/6 of t. Then we find that after 6 rotations and in combination with the translation, we will be able to come back to identical position. Original lattice point we are able to reach it, but it has been shifted by a lattice translation vector. Okay, that is how it can be done. So this also, if you take a 2-fold rotation, it is possible in a lattice, because this is not possible in a point group, but it is in a space group when we consider positions of atoms. This sort of translations, this sort of symmetry is also possible. Okay. If it is considered for 2-fold, there is only one is possible, 2, 1. That means that 180 degree rotation and translation by t by 2. 3-fold if we consider it, okay, there is 120 degree rotation and a translation, then another 120 degree rotation. So it can be 3, 1 or 3, 2. There are many combinations which are possible. Because I do not want to go into a detail of this one, because if it has to be done, it should be done in a separate crystallography class where all these things could be explained at length. Okay. But essentially these are all the symbols which are being used. So in this slide we can see that if it is just a mirror which is there 2-fold, we can see that it is a 7 which is getting just reflected. This is how at different lattice points the motifs will be kept. Now if we look at a 2-1 rotation, okay, this one is rotated by 180 degree, it comes here, another rotation and a translation, it is brought to that point. Okay. Similarly for 3-fold, 3-1 as well as 3-2, how a motif will be rotated and translated around the screw axis, it is depicted in this figure. Okay. From this we can understand that in the 3-1 and 3-2, one it will be a clockwise rotation and a translation, another is an anti-clockwise rotation and a translation, both of them. Okay. This is the difference between these two. Though the pitch remains the same, the angle of rotation is also the same, but the sense in which it is being rotated is different. Glide, if we consider it, okay, this has mirror plus translation which is there. Glide is nothing but a mirror plus translation. I had already explained glide, okay, but what is essentially important is that if the glide is along the A axis, the symbol which is being used to represent in the crystallography table is A, okay, and the translation which is associated with the glide is A by 2. B will be B by 2. Similarly, we can have a glide along the face diagonal or on the body diagonal, which is called as a diamond glide. Okay. If there are no translation which is involved, then it becomes just a mirror operation. Okay. All these various types of operations and symbols, what is the translation vector associated with different types of glides is given in this transparency. Okay. So far what we have considered is different types of symmetry operations, which are, that is glide and screw, which are symmetry operations which involve either rotation and translation or reflection and translation. Okay. Now like we have represented in planar lattice, how do we represent all these symmetry elements? Okay. First what we have to do it is that some projection will be required. Okay. Suppose we take the example of an orthogonal, example of a orthorhombic lattice. How are we going to present orthorhombic lattice? If you look at projection of one particular plane, okay, that completely does not represent the orthorhombic lattice, right. So at least 2 projections are minimum required to complete it. If it is a cube, 1 projection is good enough. Okay. So, depending upon the type of crystal structure, different projections are required, okay, graphical projections are required to show that this is what essentially is the planar lattice corresponding to that in a particular direction, correct, or the units corresponding planar units. That is essentially what is being, when we represent it, how are we going to show at what position they are going to be there, and so that is what essentially is being shown here. Like if you take in this particular one where it is nothing but a tetragonal lattice, in this particular tetragonal lattice, the projection if we see, this is the in this plane which we show, and the atom at the next plane will be projected to the middle, and the next plane is essentially identical to this one. So, this can be represented as having coordinates half, 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 or in this projection it can be just shown at all these xy positions are there, only the z position is half. This way also it can be shown. This is what is being generally used, this sort of projection in the case of space group symmetry when we represent it. Okay. Now, just let us have a look at the different type of how it is space group is presented in the International Union of Crystallography table. Okay. One, if you look at the table, at the right hand side they will show what is the crystal system, then what is the point group symmetry which is associated with it. Okay. Then the Schoenfly symbol also will be shown, which I had not just shown here, because that is the symbol which is, because this particular type of a space group symbol is essentially is the one which is now conventionally adopted in crystallography, but still people who use crystal chemistry, they use the Schoenfly symbol because that is one easier to work with when we consider it as different group symmetry operations. Okay. Then that one number is given, this gives the what is the space group number, okay, and then what is called as a Patterson symmetry, which talks something about that diffraction, it is something related to a diffraction symmetry. Okay. These are all the information which is being given. Then next, what is the information which is being given is essentially the unit cell, okay, and this is the unit cell one projection, okay, and in this projection what all the symmetry elements, this is for a P2, means that only one two-fold rotation is there, and the detailed symbol if you look at it, P2 is 1, 2, 1, that means that along x axis one fold rotation, two-fold is along the y axis, and one fold along the z axis. Okay. Now, this is the, and then it is being marked 0 to A, this is that x direction, and this is 0 to C, okay, B direction is perpendicular to it in this specific case. And then not only this is being shown, in the other two directions also, how the unit cell looks like and the symbols which are associated with it, because this symbol which is being used is represents that there is a screw axis. Okay. And generally afterwards you show a unit cell, okay, how the atoms are placed, okay. In this particular case, okay, since it is only one fold axis is there, the origin could be chosen anywhere. Okay. If different symmetry elements intersect, origin gets automatically fixed. Like if only two-fold rotation is there, where do you fix the origin? Arbitrarily we have to fix it. So essentially the origin is fixed, okay, and on that the projection of the unit cell is being shown. Now when you place a motif, the motif is placed, where is it being placed? At some position, okay, above it. That is why it is being shown O plus. Plus indicates that it is at some particular value, it is above this plane of the unit cell. and from here by around this axis is a twofold rotation. Okay. So, what is going to happen is that it gets twofold rotation and this side it comes again O plus, this is how the general position is being shown. This is how the graphical representation which is given for a monoclinic lattice. Okay. Then as we can see here, there are many symmetry elements which are associated with it. What are the symmetry elements which are, this point has one unique symmetry, this is another one, this is another one, this is another one, because from this point to this point it is a lattice point, so that is the identical. But these are all the new symmetry elements which are generated in the unit cell. So, we can put atom or the motif at this position and this position or at this position. So, essentially that is what is being shown. One, this corresponds to 0 y 0 is it is being placed on this axis, and another is 0 y half, okay, half position. This is corresponding to here, and this one corresponds to, no, this is, yeah, half this position, and this corresponds to one at the, and this corresponds to coordinates where the motifs are being placed with respect to a general point. Okay. So, this is the table which is very important for constructing the crystal structures. Okay. Along with it, we should know what the lattice parameters are. If this information is available, we can construct the complete crystal structure. Okay. If you consider in this one, there is a screw axis also is possible, the 2 instead of a mirror rotation associated with, there can be a translation. So, it could be a screw axis. Then the symbol which is being used is this particular symbol. Again, if you look at the symmetry elements which are associated with it, it is an identical type of a symmetry element which you see it. Okay. And in this particular case, okay, the symbol which is being general point, that is at where there is no symmetry is associated with it. If you put a motif at a height, some height y, okay, then after 180-degree rotation, it will come at a position that, but it is shifted up by plus half. That is exactly what is being shown. And then the coordinates, if you see it, here we can represent the coordinates this way, correct? These coordinates also, there is another representation in which it is being done in crystallography table. Okay, I will not go into the detail of it. Now let us look at P4 mm. Okay, here it is a 4-fold symmetry. 2 mirrors are also associated with it. Okay, the way in which it is represented is that these are all the positions of 4-fold symmetry lattice points. Then here we have 2-fold, then mirrors which are there. The motifs, these are all points, if we keep a motif at this particular point, it is lying on a mirror. So, it is called a special position. If you put it here, it has a symmetry which is 2 mm. So, this is a special point. And if I put a motif here, it is lying at a general point. So, each of the position, what will be the coordinates, that is the information which is given in this particular table. Okay. Using this table, okay, and essentially here again, like as I mentioned for 2-dimensional lattice, what are the various positions at which the motifs will be kept for different, associated with different symmetry elements. Okay. So, in short, if you look at it, okay, the general position where we put it has got 1-fold symmetry. The special positions in the unit cell, okay, there we have many symmetries which are associated with it. Depending upon that, the multiplicity will change. Okay. So, the crystallography table, if you look at it, the graphical representation shows the unit cell, okay, associated with all the symmetries associated with it, and then a general position which is represented. Then in addition to it, in another table, all the positions of the special positions and the general positions are also given. Okay. So, the latter part of that information is what is necessary for constructing a 3-dimensional crystal. Okay. This I have explained it with a few examples, but when we have to look for the actual crystal structure, all these things have to be specific positions have to be considered. In the next class, we will take some examples and explain, okay, how different types of structures can be constructed using the information which is given in the space group table.